Hey guys, welcome back to quantum mechanics. Hope everybody's doing all right. Today's going to be kind of a quick one. We're actually was looking at the schedule from last year, and we're already actually about a week ahead. So we'll have a couple short classes here in the next couple classes, and I'll get a homework assignment out there and get you working on some perturbation theory, and so we can take it nice and easy for the next week or so, um, and stay on schedule. Okay, so last time we were finishing up our discussion on time-independent perturbation theory, the formalism of the theory, and we had finished. We were talking about the first-order corrections to the energy eigenket, and we were showing that really to all orders, these corrections have to be orthogonal to the ground state, or sorry, to the unperturbed state for perturbation theory to actually work. Okay. And then we went on and started, we talked a little bit about second order terms. In particular, we focused on computing an expression for the second order correction to the energy. And so we started with our full eigenvalue equation and expanded everything out, and then matched terms to order to second order. And again, dotting this arcs, the resulting expression from the left with one of the eigen bras of the unperturbed ket allows us to evaluate this term here. And when we do that, a lot of stuff cancels out. So we get some cancellations, we get stuff dropping out because these corrected eigenkets are orthogonal to the unperturbed kets. And basically we get one surviving term, which is this matrix element of the perturbation Hamiltonian between an unperturbed ket and the first order ket. So as a first check, we see that this thing is order or second order because this is the first power, this is first power. Remember, those powers add. From there, we inserted a complete set of states, right, where we allow for m to be not, or we're basically saying m is not equal to n here. And we can expand that. And the reason we did that is because earlier we had an expression for this guy, this coefficient here. And we plugged that in, and we noticed that these two terms are Hermitian conjugates of each other, so we could write it a little more compactly like this, where this is the matrix element H1. It's a non-diagonal element, so you notice that it's m and n, and here m can't be equal to n. Okay, and it gets squared, and to get the units right, it's divided by the difference in the energy between those two states. So from there we went and studied a very simple problem, and it was a simple problem that we could solve exactly and then expand. So it's a problem where it's a two-state problem with some non-diagonal terms, and we were assuming that this parameter lambda was small. So we were able to solve that problem exactly and then expand, do a Taylor expansion around about this lambda parameter. And we were able to find two approximate expressions for the eigenvalues or the eigenenergies. And so this is what we found by doing that. And then we went on and applied our perturbation theory directly to this problem by splitting the Hamiltonian into a simple piece, which is just the two diagonal terms, and then the small piece, which is the non-diagonal terms, right? And then we were able to just straightforwardly apply our expressions from our perturbative theory. And so to first order, we found that these non-diagonal terms obviously vanish when you sandwich them between identical terms, so the diagonal corrections are zero, right? And we could have guessed that when we got back here that we should have known that we were going to have to start at order lambda squared anyways. So that's what. So we did that for E1 and E2. Both of them we found that the first order corrections vanish. So we had to go to second order, and that's what we did. So we took our H1, we plugged it in. Remember, this matrix element's squared. So you evaluate these products, right? And then what's left after you square it is just a lambda squared V1, 2 squared for both E1 and E2. To be a little careful because of the formalism. The subscript here is the subscript of the first term here in the denominator. So when we were solving for E2, what E2 was the first term. So to match with what we had earlier, you had to pull out that minus sign to get the E1 minus E2 in the denominator. Okay, but when you go back and you look and compare it to the exact result that we expanded, you see that it's exactly what we got. So that was good news. That was our first kind of experience with perturbation theory, and we see that we're matching on to the exact theory when we expand it. And we noted that that's where I was. That as we vary lambda between 0 and 1, and we're assuming that lambda is between 0 and 1, it's some small parameter. You see that the eigenenergies, or those corrections to the eigenenergies, they basically push each other away. They never cross. Okay, and that's called the no crossing theorem, and it applies to all cases in perturbation theory. Okay, so what I want to do today is to continue looking at perturbation theory, time-independent perturbation theory, non-degenerate time-independent perturbation theory, and talk about another problem that we can solve exactly, but this time we're going to go in opposite order. We're going to first apply perturbation theory, and then I'll show you how to solve it exactly. Okay, so this is a good problem that might show up on a qualifier. I mean, that's a good. I like this problem. Okay, so we're going to consider a charged particle, and this particle is going to be subjected to simple harmonic oscillator potential, right? And this charged particle is in an external electric field. Okay, in the field, the electric field has some magnitude that I'll call little f, and this is for simplicity. Consider a one-dimensional oscillator, and we'll put the field in the x direction. So x is the direction that the oscillator moves in. Okay, so we need to write down our full Hamiltonian. Right, our full Hamiltonian will be the simple harmonic oscillator Hamiltonian plus the term coming from the interaction of the charged particle with the electric field. Okay, so here in this case, the simple piece, the simple Hamiltonian, is going to be the one from the simple harmonic oscillator, right? So it's just going to be the kinetic term, and then the usual simple harmonic oscillator potential, right, the x squared term. And the small piece, right, the small term, or the term that makes this problem difficult, or more difficult than the simple harmonic oscillator, is coming from the interaction of the charged particle with your field. Okay, and note that it goes like the position coordinate x. Okay, so here F can be some, F is some electric field that we can ramp up, but Q is going to be our small number. Q is going to be the number that we expand around, much like we did lambda in that earlier case. Okay, so and if you're a little rusty on your E&M, sketched out how to go from the electric field to the potential energy, and that was more from my more for me than it was for you guys, hopefully. All right, so let's take this problem and apply perturbation theory to it. And we're working with simple harmonic oscillators, so we want to work with the simple harmonic oscillator kets, right? And so that means that we're going to want to take, when we compute matrix elements of this H1, we're going to want to convert this X into its form in terms of A and A dagger, the raising and lowering operators. Okay, so if you're rusty on that, go back and check it out. But hopefully that stuff is, ingrained into your brain. Okay, so let's compute the first order correction, right? So I have my unperturbed energy plus the correction, right? And the correction goes like x to the first power. And if you remember anything, the expectation value of x with respect to these unperturbed states is going to be 0, right? Because the A is the annihilation operator. It's going to destroy this state, and this guy is going to destroy that state. Well, I'm sorry. Let me take that back, because these aren't the ground states. They're just unperturbed states. But what happens is this guy's going to lower this state. This guy's going to raise it, right? And you're going to get orthogonal terms, or orthogonal bras and cats hitting each other, and that's going to give you 0. Okay, so that's why this term vanishes. So we can move to second order, right? And in second order, I need to compute H1, but in between M and N, where M and N are the unperturbed cats. Okay, so now we can see that there will be some non-vanishing terms in this case, because M can be, it could be N plus 1, N minus 1, so on and so forth, right? Because we're summing over all values of N except M equals N, all right? So what we have is the expectation value of A dagger, basically, right? So I'm applying A here. That gives me this N0 minus 1. And I get the prefactor, this factor square root of N. And then the A dagger is going to give me this N plus 1. And then I get the factor of N plus 1 out in front. Right? And these guys we can write as Kronecker delta functions, right? And M naught and N naught minus 1. And this guy is M naught and N plus 1. Okay. The nice thing is that, so we have this matrix element, and the next thing we have to do is square it. But you can convince yourself that when you square this thing, it's basically going to give you only this term squared and this term squared are going to be the only non-vanishing ones, because when you dot these two in together, it's going to give you a delta function in N naught minus 1 and N naught plus 1. And I'm no mathematician, but those two can never be equal. All right, so that cross term is always going to vanish in that case. Okay, so we've got the matrix element squared. Right, it goes like N naught, this delta function, and then this square root shouldn't be there. Should be N naught plus 1 times this delta function. Okay, so we plug that in. Right, so I've got the energy here is equal to the unperturbed energy, and here's my sum over the term. So here's the sum where M naught, or here's the term where M naught equals N naught, or yeah, where M naught equals N naught minus 1. Sorry, right. So you can see the subscripts here tell you what term it is, and here's the M naught equals N naught plus 1. Right, so I get this difference here. Okay, and here's my QF quantity squared, and this factor of h bar over 2m omega is coming from the definition of x in terms of A and A dagger. Okay, so next step is to plug in. These are the energy eigenvalues of the simple harmonic oscillator, so we know what those are off the top of our head, and they're just the difference in between two neighboring states, right? So it's going to be the magnitude of the difference is going to be h bar omega. Here I've got a higher state, and I'm subtracting a lower state, so it's going to be plus h bar omega. And here I'm subtracting a higher state, so it's going to be minus h bar omega. Okay, and then from there I can just simplify things, and you see that this N naught's going to cancel out, right? And I end up with something that looks like this once I put all the terms together. Okay, so what we would call the energy shift, and the energy shift is the difference between when you subtract the unperturbed energy over onto the other side. It tells you just how much you're shifting away from the unperturbed state, right? And typically it's called delta N, but you might see it called delta EN or something like that. Just be careful that if a problem's asking you for the energy shift, or if it's asking you for full first order energy, which in that case you would include the unperturbed energy as well. Okay, so in this case, the difference is this. All right. So, like I said, we've got the second order energy eigenvalues, and now what I want to do is show you how to solve this problem exactly, because you can solve it exactly, and it'll give us a kind of a testing ground, because we'll be able to solve it exactly and then expand, and we'll be able to see that the results agree with our perturbation theory results. Okay, so in the exact solution, you put all this stuff on the same line, and anytime you see something like this, x squared, and then this term that's linear in x, this thing is begging to be, completed, right? To complete the squares, okay? And so that's what we're going to do. So we're going to pull out a common, or pull out this factor of m omega squared over 2, right? So that I get the x squared term with a coefficient of 1. And that leaves me with the coefficient of x being this thing, 2qf over m omega squared, right? And to complete the square, I need to take half of this thing and square it. But I can't forget about this prefactor out here, okay? That's a common mistake. All right, so I take half of it and square it, okay? And I get this, so I would get this, but I need to add and subtract it. Let me see if I can get rid of that. No, I don't know how to get rid of that thing. Let me just, yeah, there we go. So you can see I've just added and subtracted this term, right? And that's going to allow me to complete the square, okay? So I get something that looks like this. So here's my kinetic term, potential energy term. You see that the x variable is being shifted by some constant piece, right? This is a constant term. And then subtract it off. We're subtracting off some other constant term, all right? So this Hamiltonian, if somebody just handed it to you, you can, think of it in terms of classical physics, really. It's a harmonic oscillator. It's got the same frequency as the one the unperturbed one, if you will, right? It's got the same frequency, but it's centered at not 0, but at QF over m omega squared, right? So it's been shifted from being centered at x equals 0 to being centered around this point, right? And then also we see that it has a constant energy term that's being subtracted from it, which is this leftover piece from completing the square. Okay. So basically, you can look at this problem and you can write down the solutions because you can see that the eigenfunctions of our full Hamiltonian are going to be the eigenfunctions of our unperturbed Hamiltonian, right? And they're going to be shifted by some constant piece, right? So we're just which is basically coming from the shift in the x variable, right? And the energy eigenvalues are going to be just the unperturbed energy eigenvalue of the simple harmonic oscillator minus that constant piece that's coming from here in the Hamiltonian, okay? And you can see when you take this and you compare it back to what we had over here, that sure enough, we get the same result, okay? So again, this is a good problem to test you on as far as perturbation theory goes, or time independent non-degenerate perturbation theory. And it's a problem I've seen a couple of times on the qualifier because you can solve it exactly. Okay, just remember this trick of completing the squares. All right. Okay. So the next example I want to consider is it's a little closer to a real world example. Okay, this is something called the Stark effect, or more specifically, the quadratic Stark effect. I think later on we'll study something called the linear Stark effect, but for now let's focus on this guy, okay? And as you're going to see, as we move closer and closer to real world problems, it kind of, it's to our advantage to look for shortcuts, and to look for ways that we can, get around. I don't want to say get around, but the way, we can use our intuition, our quantum street smarts, if you will, to try to, uh, have an idea of what the solution is going to look like, right? So let me just show you some examples here, and you'll hopefully understand what I'm trying to say. Okay, so one of the ways that we reduce a lot of the labor when we're computing these things in perturbation theory is through the use of so-called selection rules. Okay, so these selection rules basically tell us, what types of transitions can take place, right? Whether they be, physical transitions from, one positional state to another positional state, or if they're more selection rules as far as like energy eigenstates, right? So, you might have some atom that's in a particular state, and due to some selection rule, you know that it can't decay down into one other particular state. It can only, because of these selection rules, which typically come from symmetries of the Hamiltonian, uh, uh, it restricts, the type of transitions your state can make. Okay. So these selection rules are based on the idea that if you have some operator, some observable A, that commutes with the perturbation Hamiltonian, then you know that the matrix element of H1 in this basis is going to be 0, unless you're talking about strictly strictly an expectation value, right? Where A double prime would be A prime, right? And to see that, you can take this expression directly, right? Or take the commutator directly and write it out, and then hit both sides from the left and right by A double prime and A prime, right? So what happens is A can hit over here and give you an A prime, A can hit over here and give you an A double prime, and you're left with this thing, A double prime minus A prime, and then this, right? And that basically proves that this guy has to be 0 unless A double prime equals A prime. Okay. So one particular example is where the perturbation Hamiltonian is lambda, some small parameter, times z. And here z is the position operator z in the in the z direction. Okay, so this is like it's z because we're leading up to working with hydrogen atoms, and we always pick the z direction to be special because of the LZ operator. All right, so so z is pointing in the z hat direction, right? And so this operator, we can already tell it's H1 is going to commute with z, obviously, because it's proportional to z, right? So this thing is going to be invariant under rotations about the z-axis, right? That also implies that LZ commutes with this Hamiltonian, right? Because LZ will commute with z, right? And so that means LZ was going to commute with H1. That means that we can replace, these generic labels, A double prime and A prime, in our particular case, with the eigenvalues of the LZ operator. So let's say M1 and M2, right? So if we have something that has, here the perturbation Hamiltonian is pointing in the Z direction, and we see that we have basically azimuthal symmetry. So we have symmetry about the z-axis. And you guys can't see me, but I was just doing the right-hand rule. Okay. Hopefully everybody's doing that as you're watching the video. And so we're labeling the states by the LZ operator, and so we know that this guy vanishes unless M1 equals M2, right? So this is an actual example of a transition rule, right? Okay, so what about a more interesting case where H1 is parity invariant? In other words, let's say H1 is proportional to Z squared, right? So then when I operate on this with the parity operator, in other words, I invert space, this thing is invariant, okay? So what that's going to tell us is that this, the matrix element of this guy, so nothing changes with what we said before, but the matrix element between states of opposite parity is going to be 0, right? Okay, so how do we physically interpret this kind of statement, this kind of rule for transition rules, right? Um, so one way you can think of it is the fact that A commutes with H1 tells us that, and these I'm doing air quotes now, H1 carries no A, right? So if you think of it in terms of what's a good example? If I'm trying to think of a physical example. Let me move on, and I'll hopefully come up with something. Okay, you'll see what I'm talking about here in a second. Okay, so what it's saying is, when this thing acts on a state, it's not imparting any A, right? Where A is some observable. Okay, so that means that, in other words, if I hit H on an eigenket of A, it's not going to change that state. Okay, and this is something that we already know, because this is telling us right now that the eigenstates of A and H are compatible, right? If you guys remember from last semester. Okay, so let's consider this state A prime, right? And A on A prime gives me A prime times A prime. It's this eigenvalue equation, okay? And let's say we'll take a state, we'll hit it with our perturbation Hamiltonian, and then we'll do a measurement of A. Okay, so we already know that it's in this A prime state. So I do that, so I hit H on A prime, and then I do a measurement with A, okay? And so I can take these parentheses away. Remember the associative axiom of quantum mechanics. And then the fact that these guys commute tells me that I can move A through H1 onto this A prime ket, right? And when A hits A prime, give me a value A prime, a number I can pull out, and then I can put the parentheses back in. And when I look at this, it's telling me that the eigenvalue of A prime hasn't changed, right? From even though H1 acted on it. So in that sense, H isn't carrying any A, if that makes sense. I hope it does. It makes sense in my head, but maybe it doesn't. It's not imparting any A, whatever A is, onto the ket. Okay, so we see the eigenvalue is the same before and after that action of H1. What am I trying to say here? The selection rule then just reflects the orthogonality of the eigenstates with different eigenvalues A prime. Yeah, I think that's pretty. Yeah, this is pretty straightforward. Okay. So a real world example of this, and I won't go into this in a lot of detail. I used to, but it just confuses the hell out of people. And it's easier just to. This is one case where I would just encourage you to just remember the formula, okay? This is a case where H1 does carry A. Okay, so this is where H1 carries some quantity that when it hits an eigenket of some operator, some observable, it's going to change the eigenvalue of that observable. Okay, and the perfect example is when H1 is a so-called tensor operator. Okay, so don't get hung up on this. If you want to read about it, you can go to Shankar. It's about page 417, I guess, depending on the edition that you have. So a tensor operator you might write like this, right? So it's a tensor operator, so it's going to have two indices, okay? And sometimes you'll see it written like this, Q and K, but really Q is M, the LZ quantum number, and K is the L squared operator, the eigenvalue of those L squared operators. And this thing, so imagine we have a Hamiltonian that's a tensor operator, right? So it has some term that looks like this. And what it does is it's carrying angular momentum, K and Q, or if you want, L and M, right? And so what it's telling us is that there's going to be a selection rule that is related to this Hamiltonian, this special type of Hamiltonian. And there's a theorem that tells us, that gives us basically the selection rule. Okay, so and it's called the Wigner-Eckhart theorem. Okay, so this is a matrix element between two angular momentum states, so J1 and M1, and J2, M2. And so let's just say our Hamiltonian is just strictly this tensor operator, right? And what the Wigner-Eckhart theorem tells us is that this matrix element vanishes, right, unless J1 plus K equals J2. Okay, so let me just do that again. J1 plus K equals J2. So in other words, this operator is imparting some K, some value of K angular momentum onto this J state, right? And likewise, M2 has to be equal to M1 plus Q, right? And because J here is the L, like a J squared operator or L squared operator, it can take any value between J1 plus K down to J1 minus K. Okay, so I should have said that from before. Okay, so it's just the normal addition of angular momentum. Okay, so that's maybe one of the most famous type of selection rules, and we'll come back to it a lot as we compute these things in perturbation theory, especially when we get to like hydrogen-like atoms. Okay, so that does it for today. I will definitely put a homework in the Dropbox soon, maybe tonight. I'll have to see if I can find it. But I'll let you know, and you guys let me know if you ever have any questions or problems with anything. I will be up to date on the notes in the Dropbox. If you have any problems with that, just let me know. All right, guys. I'll talk to you later. Bye.